Hi, I'm Swapnanil, and today I'm going to talk about Wheeler-Feynman absorber theory. Okay, so here's the problem. So you have an electron that's oscillating, okay, that's jiggling or oscillating, so it emits electromagnetic radiation, right? That's what an accelerating electron does, okay? When it accelerates, it emits radiation. Now, as a result of that, the electron slows down, okay? So the question is, what is that resistive force, okay, acting against which the electron slows down, okay? Because when something slows down, it means that there's a resistive force, okay? So to explain the origin of the resistive force, Feynman, okay, first assumed that an electron cannot exert a force on itself, okay? So an electron oscillates, okay? So it's not possible for it to exert a force on it, okay? So it sounds like a trivial statement, but I mean, there are arguments about, different parts of electron exerting forces on each other, and they calculated the net force and so on, but that didn't quite work out, this approach, okay? So Feynman assumed that, okay, just forget it, okay, an electron cannot exert a force on itself, okay? So the question is that, where does the force come from, okay? So Feynman assumed that it's the other electrons in the universe, okay, that exerts a force on the jiggling electron because of which it slows down, okay? So he called this electron as the source electron, okay? And all the other electrons in the universe, okay, what does that mean? It means, there are electrons, right? I mean, in matter everywhere, okay? So he called them absorber electrons, okay? So it's like this electron, for example, this is an electron, okay? It's an absorber electron, all right? So Feynman assumed that when this electron, the source electron, jiggles, it sends out a radiation, okay, which falls on, let's say, an absorber electron, and makes that one jiggle, right? So because radiation is like, you have an electric field, it means there's a force acting on the electron, okay, and causing it to accelerate, so which in turn, this electron then radiates, okay, back. So when this radiation reaches the source electron, then this feels a force, a radiative force. So, so you can account for this type of, sort of back reaction by all the absorber electrons and calculate the net force, okay? But this theory that Feynman, he was then a graduate student, the theory that he proposed had a flaw, okay? Which is that, it takes a finite time for the radiation to go and then another radiation to come back, okay? Whereas in reality, the force, the resistive force is instantaneous. The moment an electron starts to jiggle, it feels that resistive force, all right? So Feynman took his theory to his advisor, Wheeler, who then remedied that problem, okay, by suggesting that they use something called an advanced wave. So Wheeler assumed that in addition to the standard radiation, okay, every charge has an advanced wave associated with it. By advanced wave, it means that a wave that comes from infinity, okay, before the charge starts to jiggle and sort of collapses on the charge just when the charge or the electron starts jiggling. All right, so to kind of imagine it as a spherical wavefront that's coming toward the charge when the charge is at rest, but the moment the wavefront collapses at the location of the charge, it just starts to jiggle. Okay, it's sort of counterintuitive. It's sort of hard to intuit it because we are used to the retarded wave, right? The retarded wave is like a charge starts to jiggle now and the wave propagates, okay, in future time, okay, something happens now and its effect is felt at a distance at a later time, okay, that's called retarded wave. But this is a different type of wave. This is called an advanced wave. Let's actually draw let's try to understand the advanced wave, okay, in somewhat more detail, all right? So let's say this is your absorber charge and it starts to jiggle, okay, at time t equal to 0, okay? Now, at earlier times, like let's say at t equal to -5, at t equal to -3, and so on, okay? You have this spherical wavefront, all right? And it's kind of gradually collapsing, okay, to the charge at t equal to 0, just when the charge starts to jiggle, all right? So you can think of it as a kind of collapsing wavefront, or you can think of it in terms of a wavefront that's diverging, right? But if you take the latter view, like it's diverging from this point, then you see the wave goes backward in time. Like it starts at t equal to 0, and then t equal to -3, t equal to -5, and so on. Okay? So advanced wave goes backward in time, all right? In that sense, okay? But I kind of prefer this other view, like, it's coming, it's kind of shrinking to a point, okay? From the past to now, okay? It's coming to this point. But the astounding thing is that, it happens before the charge starts to jiggle. So the idea was that Wheeler suggested was this, that yes, so he accepted this Feynman's theory that, it happens, the whole thing happens because this is jiggling, this charge. So it sends a radiation, okay, retarded wave, okay, it reaches this point, but by that time, before it reaches this point, this charge has its own advanced wave, which is kind of collapsing, all right? And it collapses to this point just when this charge, this electron, starts to jiggle, all right? And they explain the radiation resistance through the advanced wave of an absorber electron. Like if you can think of a wavefront that is like this, and that passes through the source electron at t equal to 0, just when this charge starts to jiggle the source electron, okay? And it's that force, okay, the force because of the advanced wave, that the source electron feels, okay, that gives the radiation resistance of the source electron, all right? So it's so they explained the radiation resistance, like the resistive force that the source electron feels, okay, right when it starts to jiggle in terms of the advanced waves, okay, of the absorber electrons, means all other electrons, okay, than the source electron, okay, all right? Okay, now let's kind of get into the sort of the details. This is, this kind of looks like a sci-fi, right? Like it's like, it seems too unreal, right? So let's actually get to the mathematics of it, okay? So maybe that will give you some confidence that the whole thing has a mathematical, basis, all right? So let's write down the expressions. So I'll start by writing down the expressions of a retarded wave and an advanced wave, okay? I'll take it from there. All right, so let's write down the expression for the retarded wave of an oscillating charge first, okay? Let's say this is a source charge, okay? So what is the expression of the radiation wave for this charge at a distance r? So first of all, the radiation is this way, okay? It's directed perpendicular to the line joining the charge to the point in question. So this point is kind of far away from the charge, all right? So it's given, so what does it depend on? What does this electric field depend on? It depends on the acceleration of the charge, okay, A0, I'll call it, all right? And it falls off as the distance, okay? So that's true about any wave that kind of sort of, diverges from a central point, all right? So you have this factor, 1 over r, okay? And then it depends on sine theta. So if this angle is theta, then it's not this acceleration that determines the radiation field, but a component of the acceleration which is perpendicular to this line, okay? And if this is theta, then you can convince yourself that this component, the component of the acceleration in this direction, is just that, okay? And then you have e to the minus I omega t minus r over c. So I'm going to use the complex numbers, okay, for wave, all right? It's a pretty standard expression, complex expression for a wave, right? So you see, omega is the frequency, so it's the frequency of the oscillation, and you have t minus r over c, right? So that's the the negative sign denotes the time lag, okay? This is why this is a retarded wave, okay? Like whatever happens now is going to happen, okay, later at a finite distance, okay, at a distance which is farther away, right? Okay, and there is a constant because it's an electromagnetic wave, so you have a constant which is minus e over. So you have this negative e over c. Okay, so this is the retarded wave. So Wheeler and Feynman proposed that every charge has half advanced and half retarded wave. Okay, so that's where this factor half comes from. Okay, and so this is the retarded wave, and you also should have the half advanced wave, which is given by a0 over r sine theta. Now you have minus I omega. Okay, look at the difference. Okay, so instead of minus r over c, you have t plus r over c. Okay. So because you have t plus r over c, this one denotes a wave like, you know, if this is t equal to 0, then this is t equal to -3, this is t equal to -5, and so on, okay? So this is t equal to 0 and r equal to 0, okay? So, all right, r equal to 0, t equal to 0, okay? So this thing is 0, right? So now, you see, when r is positive, okay, you need a negative t, right, to make this 0. So the phase kind of propagates, you know, backward in time, okay? So anyway, so the difference between a retarded wave and an advanced wave is in, you know, in these signs, all right? And you have this factor half, you know, okay, half retarded and half advanced, all right? Okay, so at a distance r, okay, so the electric field, okay, due to the source is given by, let me write down that expression first. So minus E2 c squared A0 over r sine theta e to the minus I omega t minus r over c plus that, which is E minus 2 c squared. Once again, you can see that it's there. They look very similar, right? Except for this thing, they're just really identical, right? Okay, so these two, the signs, you know, give two different senses of propagation. Okay, one propagates forward in time, this one propagates backward in time. Okay, all right. So this is the electric field due to the source, means, you know, the oscillating charge. Okay, now I'll just show you a result that actually Wheeler and Feynman derived in their paper. Okay, I'm just going to write it down, and it's just so simple. And it's just so astounding or mind-blowing, you know, that you know, I just want to mention it right now, okay? So they derived it after, you know, after setting up the problem and so on and so forth. But let me give you the result, because, you know, it's really simple looking. So they say that, okay, so this is the key interaction, okay, between two electrons, that they interact through half advanced, half retarded wave. So they considered absorber electrons, you know, all the absorber electrons that's there. This is the source electron, you have absorber electrons, you know, all over the place. So they calculated the advanced wave of the absorber electrons, okay? And this is what they found, okay? For, you know, they calculated the advanced wave for one absorber electron, for another one, and, you know, so on and so forth, and they added them all up. And what they found was this. This is, you know, so I'll write absorber, okay? All right. Now they found that the first term is exactly the way like the source term, all right? A0 over r sine theta e to the minus I omega t minus r over c, okay? But for the second term, for the advanced part, this is what they got. E2 c squared A0 over r sine theta, and then you have e to the minus I omega t plus r over c, okay? Now, did you see the difference? Instead of a minus sign, they got plus for the absorber advanced wave, okay? So this is calculated for the, you know, not for the source, but for the absorber, you know, electrons, okay? And this is the advanced wave, okay? I should probably write that, advanced, okay? And the advanced wave looks like this. So at a given point, at a distance r, if you just add these two up, because, you know, in electric field, you have to use the superposition principle, like, you know, you calculate electric fields for all the charges and add them up at a given point, okay? That's the net electric field, okay? That's what that matters, all right? So if you add these two up, what happens is these two terms cancels out. The two advanced waves just gets canceled out, okay? So what remains is just the retarded wave, but twice, okay? You have to multiply this by twice. So, you know, the factor half, that just doubles, so you just get the retarded wave, okay? So the net field, when you add these two up, okay, these two electric fields, the net field is the conventional retarded wave that we see, okay? Like, so, you know, because whatever theory you propose, you have to explain, you know, what you observe, right, in reality. In reality, we don't see an advanced wave, okay? We see only the retarded wave, and not half, but the full retarded wave, okay? So their theory explained that, okay, that's indeed true. If you add up the electric field of the source and the advanced wave of the absorbers, then you get this nice cancellation, and you know, you just have a complete retarded wave, okay? Now the question is, you know, it follows from mathematics, okay? Very rigorous mathematics, you know, through rigorous mathematics you can prove that, okay? But let's try to understand intuitively how the absorber electrons can possibly give waves which looks like you know, it's coming from the source. I mean, because, you know, I mean, these terms, look, this expression, you know, is because of the absorber, because of those other electrons, right? But they look just like the first term. I mean, how is that possible, right? I mean, why should that be the case? I mean, there's a very nice geometric, you know, interpretation of that. So let me just try to explain that. So what happens is you have this source electron, right? That's jiggling. So you have an absorber electron, okay? And you're considering the advanced wave of the absorber electron, right? So maybe I can just use a different color. Let me do that. So this is the wave front, right, for this absorber electron. So remember, it's the you know, the advanced wave, you know, has this wave front. It's just coming toward this point, right? So for this charge, okay, absorber electron. So by the way, when I say charge, I mean an electron, okay? So I'm kind of using this interchangeably, right? So for this one, you have this. For another absorber electron, okay, so you have this wavefront, okay. For yet another one, you'll get this, all right? So, okay. So what happens is that you have a wavefront, okay. These are different wavefronts of advanced waves for various different, absorber electrons, all right? And look, they look like just, you know, as if they're centered around the source, okay? So that's why, although these are produced, for example, this is produced by this absorber electron, this is produced by something which is here and so on, when you consider them together, it feels like they're centered around the source, okay? So that's why you get to, you know, you know, they kind of look like as if they're, you know, as if they're coming from the source, right? I mean, they're not, but, you know, they look like that. So that's why you can cancel out the two advanced, you know, two advanced waves, okay, and the retarded waves just get, you know, added together. All right. Anyway, so the point is, okay, so everything works out. So we have a theory. Let me just summarize this. So we have two charges interacting with each other through half advanced, half retarded wave. Okay, the source has its own half advanced and half retarded wave. And each of these absorber electrons also have half advanced, half retarded waves, okay? But we just saw that the advanced wave of all the absorber charges, okay, add up to, you know, to the total wave of the source charge, okay, and produce a net retarded wave, okay? And it cancels out and there is no net advanced wave, all right? And that's why you don't see any advanced wave. So what is the use of this advanced wave? Although it's cancelled out in the neighborhood, what happens is, right at the charge, you know, these advanced waves produce a force, okay, you know, to the source electron, just the moment when it jiggles, okay, it's the advanced waves of all the absorber electrons that gives the right force, okay, right radiation resistance as they call, okay. After that, it doesn't exist. Before that, you know, there's cancellation, there's nice cancellation, but, you know, right at that, you know, at the location of the charge, you feel, you know, it gives that right radiation resistance, okay, which couldn't be explained in any other way, okay? But, you know, the advanced waves do give you the right amount of resistive force, okay? So let me just, what I'll do next, I'll actually derive this expression for the, you know, radiation resistance or the resistive force, okay? So I will just set up, I'll give you all the steps, okay? And then I'll not actually do the integrals, so there are some very straightforward integrals to be done, but, you know, you have to keep track of various constants and so on. But I'll write down the steps, and I'll give you the final expression. If you want to integrate it, you know, I mean, feel free to do that after watching the video. It's a, you know, it's a very nice exercise to see, you know, how it all kind of works out, okay? But I'll just outline the steps, okay? Let's do that. Let me do that. So, all right, so now we are starting to derive radiation resistance. So step one. We'll first write, so remember the picture is you have a source electron, okay, and it's and you have an absorber electron here. Let's say I'll call this electron number 2. All right, so, and there's a distance which is R. Okay, that is the picture. So the first step is to calculate the E radiation, E rad, like the retarded wave because of this source at this point. Okay, so this is given by E over c squared. It's this, old expression, e to the minus I omega t minus r divided by c divided by n. I'm going to explain this over r and then sine theta. Okay, so this is the angle theta. Okay, so you have seen this 1 over r dependent sine theta before. This is a constant. A0 is the acceleration, right? Omega is the frequency. And here, note that instead of writing the speed of light c, I wrote c over divided by n. Okay, n is called the index of refraction. Why? And also I don't have the half factor. I just said, it's half retarded, half advanced, but I'm considering a full retarded wave. Why? Why? So because what I'm trying to do now is basically I'm trying to keep track of phase, like what starts to move when. You see what I mean? Like because it's wave, the phases are very important. Okay, so it is an empirical fact that the net effect is a full retarded wave, right? After a charge starts to jiggle, right? There's no half advanced, half retarded wave, and we saw that from the from what I discussed before. We saw that the two half retarded wave, one from the source and the other from all the absorber electrons, they add up, right? And the advanced waves cancels out. So what you have is this, the net retarded, full retarded wave, really. Okay, that's what you have, right? And that's why they're considering this. And the other thing is you have a refractive index here for retarded wave, okay, which you will not see for the advanced wave. Let me explain why. Why do we have refractive index here? Because what happens is when the source electron jiggles, okay, it excites all the other electrons. It's not just one absorber electrons, right? It's going through all the other electrons, which are basically absorber electrons, okay, and they in turn start jiggling. All right, so they radiate, okay? So when it's going on its way, this radiation on its way to are exciting other electrons, okay? And they radiate, okay? As a result, if you just add up all these radiations, what happens is is the effect of light slowing down, okay? That is really why light slows down in a medium like glass, okay? So you have an incident radiation and that excites an electron, that electron radiates, so all the electrons, there are multiple electrons in the medium, they all radiate, and you add up all these radiations together, what you get is a net radiation that's moving at a slower speed, okay? That's really the origin of the index of refraction, all right? And while speaking of index of refraction, let me just write down the expression for the index of refraction. It's given as n equal to 1 minus 2 pi n e squared divided by m omega squared, okay? So let me just explain. You can derive that, based on what I described, like, adding up all the radiations, like the primary radiation and the secondary radiations from all the electrons in the medium. Based on this principle, you can actually derive this formula, okay, for the index of refraction. So n, capital N, is the density of electrons, E is the charge, omega is the frequency, m is the mass, okay? You can, we're not going to derive this here, but we'll make use of this, okay, expression. So this is the E radiation, okay, so which goes from here to here, all right? Now, what does it do? What does a radiation field do? What it does is that it's like this, and it jiggles the absorber electron. It makes it oscillate, right? And what is the acceleration of this of the second charge? Okay, it's going to be the force, which is minus E rad, and you have to divide that by the mass of that electron, right? Okay, that's the acceleration, and because you have an accelerating charge, this one is going to radiate, okay? And we are interested in the advanced wave of this charge, okay, at this location, because what are we trying to do? We're trying to find the resistive force at this location, right? So we'll write down in the next step the advanced wave for that charge, okay? That's step 3, okay? And it's going to be, now I have to consider half, okay, because the advanced wave, they don't add up because there is no net advanced wave. So you have to consider, when you consider an individual absorber electron, you need this factor here, okay? And this advanced wave is going to propagate at the speed of light c, okay? Because there is no net, adding up, effect like you see here, all right? Okay, so let me write down the expression. So this is half, and then this is your acceleration, right? Acceleration of this charge. That's what I'm going to write down, okay? And then the rest of the factors are just like this, right? So you have this minus e over c squared. Do you see, all I did is, instead of a0, this is my new acceleration, okay? That's all I did, okay? This is for that electron. So I'll use this factor, I'll use this, and then you have sine theta, okay, 1 over r. And here, I have to write t plus r divided by c. There's a plus sign, because, it is not a retarded wave, it is an advanced wave, right? So that's why you have a plus sign. Now, there's a little more to it, like this t, when you write this expression, then it means that the advanced wave is centered at t equal to 0, r equal to 0, right? That at time t equal to 0, this charge, the charge 2, right, the charge 2 starts to jiggle at t equal to 0. But it's not centered properly. This charge doesn't start to jiggle at t equal to 0. It starts to jiggle, this one jiggles at t equal to 0, and this jiggles at t equal to r divided by c, right? It takes a finite time for the radiation to go from here to here, okay? You have to account for that when you write this advanced wave. So what do? You write t minus, okay? It's actually not just c, it's r divided by c divided by n, because, remember, this is a retarded wave, and, you have to consider the net effect of, everything, of all the jiggling charges, which is effectively, changing c to c divided by n, all right? So this is your new origin, basically. Shift the time by this amount, okay? Okay, so we have just one step left, okay, to calculate the, before we do the integral, to calculate the resistive force, okay? So step 4 is like, you have to, so here is let me just draw the picture here. This is a source charge, and you have to consider spherical charges, right? Sorry, absorber charges, and, you have to, let's assume they're spherically distributed, okay? So it has a certain density n, okay? And the volume element is what? It's r squared sine theta, d phi, dr, right? That's the standard, expression in the spherical coordinates, all right? So you have to, consider that, like n is the density, and then the volume element, which is r squared sine theta, d phi. Okay? All right, so now all you have to do is just multiply all these terms together and carry out the integral. Sorry, I missed a dr here. Carry out the integral with respect to r, theta, and phi, okay? And that will give you the radiation resistance, okay? So let me write down the final expression of the integrand, okay? And, all right, which is basically, all these terms multiplied together, all right? So let me see, let me just write it down maybe on the top, okay? I'm going to use a different color. Okay, so now all I'm doing is I'm just multiplying all these terms, okay? So if you do that, then you will get this expression, like half times minus e over m minus e over c squared. I'm writing this down just in case, if you want to actually carry out this integral, because, it's kind of fun to see that you actually get, the result that you should get, okay? And the integrals are quite straightforward. I'll tell you, there's a slight trick that you used to use for the r integral, but I'll tell you what it is, okay? So let me just write this down first, okay? And then you have a0, and you have 1 over r squared, okay? And then e to the minus I omega t minus r times n over c plus r over c, okay? And then you have sine cube theta, d phi, and r squared drn, okay? I hope my handwriting is still legible. Okay, so this is EM, as you can see. Where are they coming from? Let me just very quickly, okay, you can see minus E over M is coming. Okay, you have minus E over C squared here, and minus E over C squared here, that's why it's squared. Okay, you have A0, A0. 1 over R squared, where does it come from? We multiply 1 over R, that gives you 1 over R squared, okay? And then sine cube theta, okay, where does it come from? Sine theta, sine theta, sine theta, okay? And then you have d phi, R squared dr, all this, you know, things like that. And one thing I'd like to say, okay, once you have adjusted the time origin, then you don't need this retarded thing, okay? You don't need the retarded wave, all right? Because already it's, you know, you have to kind of convince yourself that because we are interested in the advanced wave of this charge, right? That is really our interest, okay? And we got the expression, you know, got the right phase of the advanced wave here after we, you know, after we adjusted the, fixed the time origin issue, all right? Okay, all right, so this is your final expression, okay? And this n is given by this formula, okay? So this n is the same as that n, is the density of electrons, all right? Okay, so if you carry out this integral, okay, integral with respect to dr, d theta, d phi, let me write down the result. Just one more thing, this is the electric field, so you have to multiply this by minus E, okay, to get the force, because we are interested in the radiation resistance. It's a force, okay? It's just not just the electric field, it's a force. So if you do the integral, this is what you will find. It's a simple looking expression. 2/3, okay, E squared C cubed d dt A0 e to the minus I omega t, okay, which is basically just acceleration AT, okay, acceleration of the charge, of the source charge, okay, it's jiggling, right? And so you see the resistive force, let me just call this F resistive, okay? The resistive force is proportional to the derivative of the acceleration, okay, of the source charge, all right? And these constants are experimentally verified, you know, these are correct, these, you know, these prefactors, okay? Okay, so that really completes my describing, you know, the radiation resistance of an electron, of a jiggling electron. Let me just show you briefly, you know, how these integrals are done, so that, you know, you actually, I really would encourage you to actually do this integral, okay, to see it for yourself, that you actually get this, okay? All right, so let me just, you know, let me write down some of the issues, okay, address some of the issues that you might face while doing these integrals, okay? So I just didn't do it because, you know, already it's too long and messy, so I just don't want to make it even messier, okay? But let me just, you know, write down a few key things about the integrals, okay? So one is you have to use this integral 0 to pi sine cube theta d theta. I think this is 4/3, okay? And then d phi integral is just simple, you know, it's just 2 pi. And you'll see that r square cancels out, okay? So what we'll have, you'll have integral like this. You may have to do integrals like, for example, you know, when you do this integral, okay? Let's actually do this very quickly, okay? These two r square will cancel out. So you'll have something like e to the minus I omega t plus r over c times 1 minus n, okay, dr. How would you do this integral? Okay, so this is, you know, the time part can be separated, so you'll have 0 to infinity dr e to the minus I omega r over c times 1 minus n, okay. Now how do you do this integral? Okay, the integrand, you know, you can write the antiderivative rather easily, right? So the antiderivative is just going to be e to the minus I omega r over c times 1 minus n divided by minus I omega c 1 minus n, and you evaluate it between 0 and infinity. Okay. Now the lower limit is pretty simple. R equal to 0. You know how to evaluate. You know how to evaluate that. So what happens when r is infinity? Okay. You have an oscillatory function. Okay. So in physics, when you have a situation like this, when, you know, you're trying to evaluate e to the I infinity, that is actually taken as 0 sometimes, okay? Why? Because you imagine that it's like, let's say, e to the minus kr, you're trying to evaluate it at r equal to infinity. So you assume that it is actually something like this, okay? Okay, it's like minus I, k minus I epsilon. You know, there's a small imaginary number that goes to 0. Okay, that's the kind of trick physicists use. Okay, so when you set r equal to infinity, then this term, there's an exponentially decaying term, which goes to 0. Okay, so this term, but the bottom line is this is 0. Okay, so when you set r equal to infinity, you set this to 0. Okay, so you need to do this integral as well, and then 1 minus n, you can plug in this expression. Okay, for 1 minus n. Okay, 2 pi n squared over m omega squared. Okay, you'll need that. All right. So I urge you to do this integral, okay, and see that you actually get this, okay. So that proves, and this integral, I want to remind you, is that it's actually the advanced wave of all the observer electrons, okay, and they produce the right amount of force, okay, acting against which the source electron loses its energy, okay. So this is the origin of the radiation resistance of an electron. Okay. Hope you enjoyed, the video and my explanation. And thank you.